then you have R over here, and let's say you have here you have RCS plus 1 into theta s. So you will have over here that so you have R into HIS will be equal to theta. So no, sorry. Yeah. So this will be 1 by 1 plus RC into S. So this is one way of represent. If you want to represent this as your block diagram, this is one way of representing the block diagram. Also, what you can do is that you can this 1 by 1 plus RCS. So what you can do over here is that you can sort of represent that 1 by 1 plus RCS as a feedback loop, unity feedback loop with the forward transfer function of 1 by RCS. So this is one way of representing a block diagram representation of the system. This is another block diagram representation of the same system. Both will give you the same transfer function, but just that the representation or the blocks, individual blocks that is being connected in the system, they are different. So similarly, let's see the block how you can draw the block diagram of a liquid level system. So in this liquid level system, you have two tanks, two interconnected tanks are present, and there are valves in between. And so the input, so there is some liquid which is flowing in. Depending on the liquid flow, the water level is maintained in this tank, and similarly water is flowing through this valve. And there is a secondary, there is a second tank, and then finally through another valve the water is flowing out. Now if you draw the, if you write the differential equations or differential equation of describing this model, so you will have, let's say that there is a change in the input inflowing liquid. If that change is given by Q, and so this change in all these rates are given by Q, this is Q1 and here it is Q2. The change in the water level in tank 1 is H1, that in water tank 2 is H2. So you will get that H1 minus H2 will be divided by R1, will give you the rate of flow of water through this this valve. Similarly, if you want to see that, similarly for this one, there will be H2 minus 0 divided by R2 will give you the flow rate through this valve, which is equals to Q2. So you have equation number 1 over here, equation number 2 over here. Then the other two equations will be depending what is the capacity, depending on the capacity of this tank. So C1 into rate of change of liquid level in this tank will give you the difference between the inflowing liquid and the outflowing liquid. So Q minus Q1 will be equals to C1 into dH1 by dt. Similarly for this tank, Q1 minus Q2 will be given by C2, which is the capacity of this tank, into dH2 by dt. Now if you want to find so you have the differential equations describing the system. Now what you will do is that you will just take the Laplace transform. So this will become H1s minus H2s by R1 equals to Q1. So similarly, you have 4 different differential equations. So from these 4 different differential equations, what you can find out is what is the overall transfer function of the system. So the overall transfer function will be the output, which is the value of Q2, divided by the input, that is Qs. So if you find that the overall transfer function is given by an equation like this. Okay. So now what we want here is that we want to draw the block diagram representation of this system. So what we'll do is that we'll individually draw the blocks for this 1, 2, 3, 4, these 4 equations. Okay. So now let's say this is my equation number 1, this is equation number 2, 3, and this is 4. So in the first equation, you have H1 minus H2 by R1 equals to Q1. So here we'll write H1, which will go into a summing block, H1, and H2 will go in with a minus sign, H1 minus H2. That will get multiplied by 1 by R1, and that will be equals to Q1s. So this is the block for equation number 1. If you see equation number 2, you will have Q minus Q1S is equals to SC1 into H1. So Q minus Q1S multiplied by 1 by SC1 will give you H1S. So this is the block for equation number 2. Then for the third equation, you have Q2 will be equals to H2 by R2. So Q2 is equals to 1 by R2 into H2. So this is the block for equation number 3 and this is the block for equation number 4. So you have Q1 minus Q2. So in this error detector you have Q1 minus Q2 and then that gets multiplied by 1 by SC2 to give the output of H2. You will get H2 as your output. So now you have drawn the individual blocks for all the 4 differential equations that are governing your system. Now what you need to do is that you have to combine all the 4 blocks together to find the overall block diagram of the system. And for the overall block diagram of the system, so you will have Q2 as your output. So Q2 is here output and QS is your input over here, right? So now let's see how we can draw the block or how we can combine the block diagram. So here you see that Q is your input. So this will come as your first block, first part of your block diagram. So you have Q1, there will be some Q1 over here. You have 1 by C1S and the output is H1S. Now you see that H1S is the input for this block diagram. So that means this H1 will get connected over here. So you can connect this thing so this block, this individual block as the second part of the block diagram. So you have this gets connected. So you have plus minus over here. You have 1 by R1 and the output is Q1S, right? And then you see that this Q1S is coming as an input to this block. So that means you can just connect this Q1S with a negative sign to this block. So this part is done. Similarly, you see that this Q1S, now that Q1 is going as a input to this 4th block. So you have this block over here. You have 1 by C2S over here and the output is H2S. Similarly, H2S is the input for this block. So it will come at last. So you have H2 into 1 by R2 and output is Q2. Now here in this part of the block, there is Q2 is coming over here. So that means you will just connect Q2 to this block after this Q1. So this completes this loop and here there is H2. So H2 will come from this point. So this is the value of H2. So you can just connect it over here and this is the overall block diagram of your system. So from here you can find out what is the overall transfer function of the system. So is it clear till now?
Yes, ma'am.
Okay. So now you see that this block diagram, this looks a bit complicated block diagram, right? Because you have so many interconnections. There are so many feedback loops, one coming from here going to here. There is another feedback loop here. There are like 3 loops. So this looks like a bit complicated block diagram. So how can we find out or how can we simplify a block diagram so that we can find the overall transfer function of the system? So that method is known as the block diagram reduction method. Okay, so the main properties of this block diagram reduction method is that so what you can do is that blocks which are connected in can be connected in series. So these are the basic properties that if you have one block which is not being loaded or not being affected by the following block, so then those blocks like can be added or those blocks can be connected in a cascade or in series. Okay, so if you have a non-loading, so if you have a number of cascaded blocks or blocks in series which represent like non-loading components, so then what you can do is that if there is no more takeoff point or a branching happening between the 2 blocks, so what you can do is that you can combine the 2 blocks and represent it as one single block and which is given by the product of the individual transfer functions. So now we'll see the different block diagram rules that are usually there, which you can use in order to simplify a certain block diagram. Okay, so the first rule is that combining blocks in cascade. So if you have two blocks G1 and G2, so then what you can do, if there is no so in this kind of an if it is connected in this way, so you can just represent it as a single block, which is equals to G1 into G2S. So the main aim of doing this reduction is that the output of the previous block and the output of the reduced block, you can say, those two should be same. So you should combine blocks in such a way that the output of the combined block still remains same as the previous one. So here you see the output. So here US will be equals to, if there is this signal here is US is equals to X into G1, and Y will be equals to U into G2. So that means Y will be equals to X into XS into G1S into G2S. So if you have YS as your output and XS as your input, so you can just write the in between as G1 into G2. Similarly, if you have blocks which are there in parallel, means they are being being connected with to a summing point with both of them are positive sign. Okay, so in that case, what you can do is that if the blocks are connected in parallel, then you can just add the two blocks and represent it as a single block. So if you have G1 and G2 in parallel, which are coming in as both plus signs, so you can write that the equivalent is G1 plus G2 with XS as your input and YS as your output. You can see the derivation, like why you can do over here is that, so this value of YS will be equals to Y1S plus Y2S, and Y1 is equals to, the value of Y1 is equals to X into G1 and value of Y2 is X into G2. So if you write YS equals to Y1 plus Y2, so this will give you X into G1 plus X into G2. So that means that will be equals to G1 plus G2 into S. So you can represent this whole block as a addition of G1 and G2. Then the third rule is for interchanging two summing points. Okay, so if you have two summing points which are just connected one after another, in that case you can just simply interchange the two summing points, and so here the output YS will be equals to, the output here is equals to PS minus rather XS minus PS, the point over here, and here this will be equals to XS minus PS plus HS. And here you see, if I interchange, if I bring this summing point before and this summing point to, if I want to bring this summing point over here, so that means here the output will be XS plus HS, and the output over here will be XS plus HS minus PS, which is same as the previous case. This one and this one is the same. So we can simply interchange two summing points like this. Then what if you want to move a summing point ahead of a block? So now let's say in this sorry, in this block you have a summing point after this block G. Okay, so now what we want is that we want to move this summing point before this block. So in that case, what we'll do is that, so the main thing that we need to keep in mind is that we need to move the summing point behind or ahead of a block, keeping in mind that the response doesn't change, that the response YS remains the same. So that means here you see the value of YS will be equals to, here it is XS into GS plus P. Now if I want to move this summing point ahead, so let's say I move it before here. So what I need to do over here is that, excuse me. So here, what if I want to move this block ahead of this summing point ahead of this block, what I need to do is that I need to add another block whose transfer function will be given by the reciprocal of this block before which we are taking it. Why we need to multiply it with that we need 1 by GS over here? Because now you see that if I want to keep my output as same, so previously this value of P was not getting multiplied by anything. So the value of P was same. But here, once we move this block, this summing point before this block, so that means whatever is coming as an input to this error detector, that gets multiplied by GS. But in the output, we have only P. So if we want to keep the output constant, so that means we have to multiply P with 1 by GS beforehand, such that after that signal passes through this block, the output still remains P. So that means now here you will have, if you are moving a summing point ahead of a block, then you have to multiply it with a block whose gain is the reciprocal of the actual gain of the block before which it is taken. So if this is GS, once you move it ahead, you will multiply it with another block which is given by 1 by GS. Then if you do like this, then only your output will remain constant. Similarly, if you want to move a block ahead or after a block, so initially you have the summing point is over here, and now you want to move the summing point after this block. So that means now you will have, so excess, so here initially the input to this block GS was XS plus X plus P, and the output was given by X plus P into G, right? So now if I want to move this summing point over here, so that means XS will become the input to this GS block, and that output added with P and something should give you the value of YS. So now you see that in this case, if you are moving it beyond or after a block, in that case you have to multiply, you have to add a block which is equals to GS. GS means which is equal to the transfer function of the block beyond which after which you are taking the summing point, so that the overall output remains the same. In the previous case, when we were moving a summing point before a block, in that case we had to multiply, we had to add a block which was given by reciprocal 1 by this GS. But if you are moving a summing point after a block, so then you will have to multiply, or you will have to introduce another block which is given by GS. Okay, so similarly you can, if you want to, suppose you have a takeoff point and you want to move this takeoff point after a block. Okay, so for moving this takeoff point after this block, what you need to do is that you'll have to add a block 1 by GS after, because here the value of P, so it is P. So if you want to keep the output of this branch as P, once it moves after here, so that means there is a P, it is getting multiplied by GS. So that means you need to nullify the effect of GS. So that's why you need a block with transfer function 1 by GS, so that the output of this block or output of this branch still remains equal to P, right? So this is another reduction rule. Similarly, if you want to bring a takeoff point ahead or before a block, in that case what you need to do is that you have to add a block which will be equal to GS. GS means which will be equal to the transfer function of the block before which you are taking the takeoff point. Okay, so these are like different rules that you need to keep in mind while you are doing a block diagram reduction. Okay. And similarly, if you have a summing point, so in this summing point, let's say there are 3 inputs. Now what you want is that you want to split the summing point and into two different summing point, and each will have 2 inputs. In that case, what you can do is that, so let's say here the output Y is equals to P plus H minus S minus X. So what you can do here is that you can split it in such a way that X is still minus, P is plus, and you split H, you take this H plus and then you make another summing point over here, but the output still remains the same. So these are like the whatever we have told till now. So this is a tabulated form of all the block diagram reduction rules that you need to follow while you are doing any kind of reduction. So you need to remember what if you are combining blocks, then what is the rule. If you are moving a pick off point or a takeoff point ahead of a block or after a block, depending on which way you are moving the takeoff point, you have to add another gain to that corresponding path. Similarly, if you want to move a summing point before a block or after a block, depending on where you want to move, accordingly you will have to add a separate block. Okay, so this is just a tabulated form. Just keep in mind like how when you are combining two blocks or when you are moving or playing around with the takeoff point or the summing point, then if you are changing the position, interchanging the position, then what should be the corresponding equivalent block diagram. So now the steps for doing block diagram reduction. So this will be more clear once we do a few examples. So the steps for doing the block diagram reduction is that first of all, the first step is that if you have blocks which are connected in series, you take them connected in series, as in there is no interconnections or there is no takeoff point or summing point between the two blocks. If they are just connected in series, you combine those blocks and write the equivalent take an equivalent block. Similarly, if you have blocks in parallel, then you combine those blocks and then you simplify the block diagram. Then the third step is that you check whether there are any kind of feedback loops present, simple feedback loops present in the system or not. If there is a feedback loop, then you can represent that portion of the block diagram with an equivalent transfer function of the feedback loop. Now then comes that there might be problems coming because of the takeoff point and the summing point. So if you see that because of the presence of a takeoff point, you are unable to simplify unable to simplify two blocks or combine two blocks and come up with a single equivalent block diagram, then what you do is that you shift the takeoff point. Generally, it is seen that if you shift the takeoff point to the right, then it becomes easier. But this is not necessary that you have to shift the takeoff point to the right. It depends on which way your block diagram is connected. Accordingly, you will either have to shift the takeoff point or the summing point to the right or the left. And you continue doing these steps until and unless you get a simplified form. Simplified form means that the overall block diagram is represented by a single block. So you have just the input and the output, and the overall block diagram, the transfer function, is represented by one single block. So now let's do an example, then it will become more clear to you. So let's say that this is a block diagram which is given to you. Some interconnections, there are so many loops, there are multiple summing points and all. So what you need to do is that you have to find out on the final block diagram where you will have only RS as your input and you will have some block as your output, and the output is CS. So this is the final goal, and you have to find what is the value of this block. So this is the final aim, you can say. Okay, so in order to represent the whole block diagram, you have to you want to reduce the block diagram and you want to find the equivalent block transfer function of the overall system. So now here you see that if you want to you see that these two blocks are in series, but there is a takeoff point over here. Right, so what you can do here, so there can be like multiple ways of doing a block diagram reduction. So in the first case, what you can do is that you can move this takeoff point beyond, you can move this takeoff point to here. If you move this takeoff point over here, then this G2 and G3 will be in series, and so you can combine the value of G2 and G3 and write it as G2 multiplied by G3. So let's see that how this can be done in a different way. So here what they are doing is that they are trying to So they are moving this summing point. You move this summing point before this block G1. Okay, or rather you moved it before G1 over here, and then you can just interchange the two summing points over here. So if you want to move this summing point before G1, so that means you will have to multiply in this loop, you will have to multiply, or you have to add a gain which is equals to 1 by G1, 1 by the block, the gain of the block before which you are moving the summing point. So that means here you will have H2. So H2 will be replaced by H2 by G1. So now your this block, this one gets moved to first here, and then you can just interchange, or you can say that this I am actually moving this whole thing from here to here. Okay, so I'm moving this summing point before this block and then before this another summing point. Okay, so here you will have, so H2 now will be replaced by H2 by G1. So you have H2 by G1, and the connection is it comes over here. Now you see that here you will have a feedback loop over here, or this is you have a positive feedback loop over here. So that means what you can write is that you can write the equivalent block transfer function of this feedback loop. So this feedback loop will give you G1 G2 divided by 1 minus G1 G2 into H1. Since this is a positive, it is going in a positive terminal. So G1 G2 by 1 minus G1 G2 H1. So this part of the block is now represented by this one single block. Now you see that this block and G3, they are in cascade. So what you can do is that you can simply represent this as a multiplication of this block and this. So it will become G1 G2 G3 divided by 1 minus G1 G2 H1. So now you have, so this part of the block, this can be represented by G1 G2 G3 divided by 1 minus G1 G2 H1. Okay, so then you see that once you have this block, and now you see that this is actually a negative feedback loop. So you can simplify this negative feedback loop also. So you will have, if you simplify these, so this is your feedback path and this is your forward path of for this loop. So you simplify and you will get the simplified version is G1 G2 G3 divided by 1 minus G1 G2 H1 plus G2 G3 H2. Now again you see that this is again a negative feedback loop, and now you can represent this or you can write the transfer function of this negative feedback loop, and this will give you an expression like this. And here this is the last step, because here you see that you have ended up with one single block, the input of which is R and the output is C. So that means that initially you had been given with a big or a complex interconnection of blocks for this diagram, and eventually by using different block diagram reduction rules you are able to come up with a single block, come up with a representation of that whole system as a single block, and this block basically gives you the transfer function of the whole system. So then this R and output is C, right? So yes.
Please, can you continue in next class, ma'am? We have a quiz now.
Oh, okay, sure. But is the block diagram reduction technique clear to you?
Yes, ma'am.
Okay, we'll do a few more examples in the next class. Then it will become like you will get more used to, or it will become more clear. So, okay, fine. So let's end today's class over here, and we'll continue in tomorrow's class. So thank you.
Thank you, ma'am.